And we're going to go through binomials again today. The only thing you're really going to miss is why are these different ways of computing probabilities than the other. But here we go. Number one, in order to be in a situation where you have a binomial distribution, remember there's three criteria that need to be met. First criteria is an experiment is repeated several times. Second criteria, you don't have to have these memorized, but I'm just going to spout them out to you again. The second criteria that needs to be met is that there's only two possible outcomes, okay? And the third criteria that needs to be met is each trial is independent from the previous, okay? The reason why these turn out a little more funky is because not only do we have to deal with the probabilities of each particular trial, but we also have to take into account all the different ways in which what we're wanting to find the probability of can happen, and that's what brought in our combinations. Okay? So, what we saw last time is that we have a really nice calculator, Fred. Okay? On your calculator, you can compute your binomial. The first number you enter is your n value, then your p, and then your x. One of the things you should have seen from last time is that your n and your p throughout each particular problem do not change. It is just the x values that change. Okay? Next, you might have a fancier calculator than I do. Yours might come up when you hit binomials EDF, and it might, the first thing that will come up is trials. That's still your n value. Okay, so just enter your n and then hit enter. And then it'll ask for the probability. Enter it as we would, and then it'll ask for your x value, and just keep hitting enter until you get your answer. Okay? Don't worry, I'm going to go through some more fairly soon. Now, we saw that the binomial PDF was a lovely way of computing this when we're given specific x values. But we also, at the end of class, talked about a reason why we might use binomial CDF. The binomial CDF actually looks and computes your probability for a whole range. So this would be for saying at most, find the probability that there's at most x. So it'd be 0 or 1 or 2 all the way up to x. Or another way you could look at it is no more than x. Do you guys remember doing that at the end of class? That was a really nice little shortcut for computing our binomials when you see at most or no more than. Okay? So it goes from that point left. All right, so that kind of sums up, at least in general, what we did last time. What I'd like to do now is start out with a specific, and then the other thing that we're going to be doing today as we play with more binomials is we're going to also learn how to compute our mean and our standard deviation. Okay? The formulas are super cute, super easy. All right, so let's start out just recapping from last time, just a basic example, okay? Oh, let's suppose 150 people are surveyed, and I don't really care. How about 93% of them like a particular candidate. Okay, now I'm going to ask some probability questions in a moment. Prior to doing that, I claim this is a binomial situation. On your quiz this Thursday, I will come out and tell you, assume it's binomial, because I want to be sure you all know how, if you know know it's a binomial to do the computations. All right? But how do we know that this is a binomial? Number one, an experiment is repeated several times. Yeah, in fact, we're asking 150 people some question about liking a candidate or not. Number two, there's two possible outcomes. Do you guys agree either people like the candidate or they do not like the candidate? And last but not least, one would assume that whether Susie likes the candidate is independent as to whether or not Mary does. Okay? So this definitely satisfies our binomial situation. So let's just find the probability that, how about part A, exactly, who knows, how about 100 people like the candidate? Can we do this computation? Oh, yes. Okay. Your N and your P are not going to change. What is N? How many people are being asked? 150. What is P? 0.93. That's another big hint that you're dealing with a binomial, you guys. It's when a general percentage is given to you. In this particular example, what is my X value? 100. All right, so I've got my calculator. I will put it on this screen. And hope that it works. Wouldn't it be worth you block? Oh, it's good. Wow, it's really bright, isn't it? Hold on. There it is. All right, much better. Okay, so how do you get there? Second bars, right? You want to get to district. Go down to binomial PDF. And you enter your N, your commas above your 7, your P, and your S. Wow, look at how teeny tiny that probability is. Whoa, 2.6 times 10 to the negative 21st power. All right, what if I want to find the probability that at least how about 148 people like the candidate? Now, I'm going to show you two different ways you can do this computation. It doesn't matter which way you choose to do it. It's kind of whichever way jives best with your brain. But what I'm wanting to do is sort of lay the groundwork for something that is coming up where you will want to use this idea. Okay? What does at least 148 mean in the context of this problem? Right, it means we're interested in 148 or 149 or 150 people. Y'all with me there? Now, if we do this the way we have been, doesn't this mean that we have 3 binomial PDFs? Right, binomial PDF, N is 150, P is 0.93, and first we have X being 148. What does OR tell us? Plus, now we do the same thing again. Your N and your P do not change, but now my X value is 149. Or, so we have another binomial PDF, and we have 150, comma, 0.93, comma, 150. Is that a pain? It is kind of. I certainly wouldn't disagree, but it's certainly doable, isn't it? Do you guys want to see what we get? All right, let's check it out, and then I'll show you an alternative way we could do it. Binomial PDF. So we have 150, comma, 0.93, comma, 148. And then you can just keep going. You don't have to do them separately unless you would like to. So then you have 150, comma, 0.93, comma, 149 plus, let's check this out. Curious what the probability is. Wow, it's still teeny tiny, isn't it? You guys with me? Okay. Now, let me show you an alternative way of looking at this. And I'm doing this not because you have to do it this way, but I'm planting a seed for y'all. Okay? So, let me say this. If we are interested in at least 148 people liking the candidate, you're right, that's 148 or 149 or 150. Can I ask you a question? What would the complement of this look like? Well, numerically speaking, wouldn't it be 0 or 1 or 2 all the way up through 147? You guys with me? Remember, the complement is everything except that event. Okay? I claim that we can find this probability with just one calculator move, can't we? Right? Isn't this where we would use our binomial CDF? Binomial CDF N, P, and then my x would be 147. Now, is this going to give me the answer to my original question? No. This is going to give me the probability of the complement. But, let's find it first, and then I'll talk about the but. Oh, shoot. Let me do this again. I went down too far. Here's binomial CDF. We have 150, comma, 0.93, comma, 147. All right, we got the probability of the complement. You guys, what's the relationship between the probability of an event and the probability of the complement? Good. Remember, everything adds up to 1. So, do you guys agree if I took 1 minus this, I would get what I was looking for? Yes. So, and again, you don't have to do it that way if you don't want to. But look, we got the same thing. Come on, how cool. Oh my gosh. Yeah. You guys with me? Cool. All right. So, I want you guys to leave a blank after my next question because we're going to come back and answer it. What if I wanted you to find the expected number of people who like the candidate? Oh my gosh, I love your question. Thank you. So, the question was, do we need to make a probability distribution table? Because remember, how do you find your expected value? Don't you take each x value times its corresponding probability and add them up? Yeah? All right. So, if we were going to make a probability distribution table here, how many columns would it be? Wouldn't it be 151 columns? Right? Because we'd have to find the probability that exactly 0 people like the candidate. Find the probability exactly 1 person, exactly 2, exactly 3, all the way up through exactly 150. Do you guys agree that that is totally an unreasonable thing to want to do? Okay? There is no way we're going to want to construct a probability distribution table with 151 columns. Okay? Hold on 1 second. Now, there is a way to do this though, but what I would like to do before I show you exactly the easy way of doing this is I would like to take you through an example. Okay? So, hold on. Just leave a little bit of space here. Okay? So, I'm going to take a really cute example, and I'm telling you it's cute because it involves cats. Okay? So, ready? Suppose a gal owns 4 cats. And the probability any cat will sit on her lap is 30%, independent of whether any other cats are sitting on her lap. All right, total binomial question. An experiment is repeated several times. How many cats do we have? 4. Well, 2 possible outcomes. Either the kitty cat sits on her lap or it doesn't sit on her lap. You agree? What's the probability that the cat sits on her lap? 0.3. And last but not least, we're explicitly given that whether or not a cat sits on her lap is independent as to whether any other cat sits on her lap. And if you guys know cats, they don't really care. They just climb on top of the other one anyway. Okay? So, total binomial. Yeah? Let's make a probability distribution table using this. This one's pretty chill. Do you agree that there could be 0 cats, 1 cat, 2, 3, or 4 sitting on her lap? You agree those are our different values of x. I'm doing this partly to motivate what the definition and the formula are for the expected value in a binomial, but partly also to give us more practice. Okay? So, in order to find the probabilities, we're just going to use our binomial. Okay? Right? In this case, my n is 4, my p is 0.3, and my x is 0. Over here, we'll compute it, and then we have n is 4, p is 0.3, but then my x is 1. Okay? Another reason why I'm doing this is just because we were doing probability distribution tables with combinations doesn't mean we can't use binomial to complete probability distribution tables as well. So, yes, we have 5 probabilities to compute. This isn't too bad. So, what do we have? So, we will binomial PDF. I have 4, 0.3, 0. And you get 0.2401. Did anyone do the 1 for 1 yet? No? What'd you get? I want out every decimal place. 0.4116. Thanks. Yeah, all of these will just be 4 decimal places. Oh, thanks. 0.2646. Anyone do 3? Someone do 3. Okay, I'll do 3.
0.0756.
0.0756. All right, and this last one should be like 0.0081, yeah. Thanks, guys. All right, all they did is this binomial thing for all 5 columns. Okay? You agree we have our probability distribution table. What if I ask you guys to find the expected number of cats on the left? Now that we have a probability distribution table, could we do this? Yes. Doesn't your formula say to take each x value times the corresponding probability and add them up? You guys with me? Remember? Man, you guys got to wake up. Well, 0 times anything, who cares about that? That's out of there. So we have 0.4116 plus 2 times 0.2646 plus 3 times 0.0756 plus 4 times 0.0081, and we're going to get 1.2. So we can expect 1.2 kitty cats to be sitting on her lap. Guys with me there? All right, tell me something. What is your n, no matter where you are in this problem? 4. What is your p? 0.3. What's n times p? What's 4 times 0.3? 1.2. So, when you're in a binomial distribution, so 4 binomial distributions, your expected value is just n times p. Isn't that sweet? Yeah. So let's rewind over here. We wanted to find the expected number of people who liked the candidate. What was my n value, you guys? 150. And my p was what? 0.93. You take 150 times 0.93, and we could expect about 139.5 people to like that candidate. Isn't that a really nice, neat way of computing your expected value? Yeah? That's exactly what you do. You multiply those, that's exactly right. But what I wanted to do is motivate it by using a probability distribution table to show you that that is, in fact, the way you do it. Your intuition's lovely. Serious. All right, the other formula I want to give you, your standard deviation. It's the square root of n times p times 1 minus p. Should we find the standard deviation for this kitty cat thing? Why not? Standard deviation. It's the square root of, what is n? 4. What was our p? What was the probability the cat would sit in her lap? 0.3. Well, then you have to do 1 minus p. What is 1 minus 0.3? 0.7. So the way you would compute the standard deviation here is you would do your square root. And what do we have? We have 4 times 0.3 times 0.7. Close it up. And you get about 0.92. It's kind of a meaningless thing here, but we can do it. Do you guys all see? Isn't this a much nicer way of computing the standard deviation than section 8.3? Yeah.
Where did you get 0.7?
Where did I get 0.7? So, do you agree my formula says n times p, and then the other part of my formula is times 1 minus p? Do you agree? 0.3, my n was 4 and my p is 0.3.
Oh,
So then 1 minus 0.3 is 0.7. Kind of think of your trees. Remember how everything had to add up to 1? Yeah. Okay, you guys ready for another example? Cool. This example will sum it all up. Yes? For the variance, you mean? I suppose if they ask for the variance, but I don't. I'm a standard deviation type of person because that's in practice what most people use. All right. So, let's do this example. The probability a certain machine turns out a defective item is 0.05. Suppose there is a run of 75 items. Let's find the probability part exactly 5 are defective. This problem is going to be the last one for the day. It's going to be very many parts, but it's going to sum up section 8.4. Okay? So, will you guys grant me that this is certainly an example of our probability being and distribution being binomial? Why? Well, something's repeated several times. What is n here? 75, right? All right, so something is repeated many times. Do you agree there's only 2 possible outcomes? Either the item is defective or it is not defective. And last but not least, whether one item is defective is seemingly independent as to whether another item is defective. Now, this problem also gets to why I don't really like the success versus failure, because what would you say your probability is here? When you say it's 0.05, right? The probability a certain machine turns out a defective item is 0.05. In reality, is a machine producing a defective item considered a success? I think not. Okay? So that's another reason why I don't really like those terms in your book, success versus failure. Okay? So what is our x value in this particular part? 5. So, can we find this probability? We certainly can. You do binomial PDF, and we hit 75, 0.05, 5. So there's about a 15% chance. Are you guys all with me here? This stuff isn't too bad, is it? Okay. What if we want to find the probability that there are no defective items? Can we do that? You bet. My n is still 75. My p is still 0.05. What is my x value in this part? 0, right? We're interested in none of them being defective. You with me? Cool. All right, so let's check it out. Here we are. So we have 75, 0.05, 0. And we get about a 2% chance. Yeah. quiz, I would have these three guys sitting right next to each other or in a row to tell you in your binomial, number one, this is the order in which you enter them. And number two, this is how you find the expected value of the standard deviation. Okay? All right. You guys with me this far? You okay? All right. Part C. What if I want you to find the probability that there is at least one defective item? Okay, what does at least one mean? 1 or 2 or 3 or 4, all the way up to 75. 1 or 2, all the way up to 75. Hello, do you guys want to compute that? No way, right? So, ask yourself, what's the complement of this? What is the complement of 1 or 2 or 3 or 4 all the way up to 75? 0, right? Isn't that the only thing we haven't taken into account here? So wouldn't it be 1 minus the probability of no defective items? And didn't we just compute that? Yeah, that was part B. There we go. Isn't that cute? Now maybe you wouldn't have thought of doing that, but I mean there is a reason to come to class. Hopefully you learn things, right? Y'all with me? Cool. All right. I have 2 more questions left. What if I want you to find the expected number of defective items in this run? Can we compute that? We can. See? It's equal to n. What was n? 75 times p. What was the probability of a defective item? 0.05. Good. So, what do we get here? 75 times 0.05 is 3.75. Any questions there? Wasn't that a lot easier than making a probability distribution table with 76 columns? I think so too. All right, one last question. What if I want you to find the standard deviation here? We can certainly do that also. Then I have one more quick comment, and then you guys will actually get out early today. Well, your standard deviation is the square root of n. What is n? 75 times p. What is p? 0.05. Good. And then that's times 1 minus p. In other words, 1 minus 0.05, which is 0.95. Are you guys all with me? Cool. Nice. Okay, so let's compute that. 75 times 0.05 times 0.95, and we get about 1.9. Okay, before I let you guys go, again, in case you came in late, your quiz is on 8.3 and 8.4. But let me show you this notation. The mean and the standard deviation. The notation from here on out that I use for my mean is mu, the Greek letter. And the notation 6